The cheapest part in your PC build might be the most important one. This is thermal paste. It costs pennies. Skip it, and a $500 processor can throttle itself into uselessness or damage itself over time. Here's what's actually happening underneath that heatsink. Ever had your PC randomly slow down under load? Fans screaming, performance dropping, and no warning at all. This is one of the most common causes, and one of the most overlooked. It's not a hardware failure. It's not a bad GPU. Most people never even check it. Maybe you've already looked at RAM, storage, even reinstalled your operating system, without ever touching what's actually causing it. It's usually a 5-minute fix that solves problems people spend months troubleshooting. By the end of this video, you'll know exactly why it matters, and exactly what to check. Look at a CPU's heat spreader. To your eye, it looks mirror smooth. So does the base of your cooler. But zoom in far enough, and that smoothness disappears completely. Under a microscope, you see peaks, valleys, tiny machining scratches, a landscape, not a flat surface. Two flat metal surfaces don't actually touch the way you'd assume. They only meet at scattered high points. Real metal-to-metal contact might cover just 1 to 2% of the total surface area. Everywhere else, the other 98%, is a microscopic gap. And gaps fill with something. That something is air. This isn't a manufacturing flaw either. It's just the physical limit of how flat metal can be cut. Here's the problem with air. It's a terrible conductor of heat. Copper conducts heat at around 400 watts per meter Kelvin. Aluminum sits around 200. Air? Less than 0.3. Picture that gap as an actual insulating layer, the opposite of what you want there. Heat gets generated constantly at the CPU die, deep inside the chip. That heat needs to escape fast. But it hits that air-filled gap and struggles to cross it. Meanwhile, the CPU is monitoring its own temperature in real time. Once it senses things climbing too high, thermal throttling kicks in automatically to protect itself. The chip slows down on purpose. Performance drops, sometimes dramatically, right when you need it most. In the worst cases, you get full thermal shutdowns. Push it further, over months or years, and you risk long-term degradation from running hot. Modern CPUs protect themselves first, perform second. That's by design. Permanent damage is worse than a slowdown. But a bad seal is silently costing you performance you already paid for and never get to use. All of that, triggered by a gap you can't even see. This is where thermal paste comes in. Think of it as a gap filler, not a magic heat conductor. Here's the part most people get wrong. Paste conducts heat worse than solid metal does. It just conducts a lot better than air. That's the whole job. So the goal isn't slathering on as much as you can. The goal is using just enough to eliminate those air pockets and nothing more. Picture a cross-section as the cooler clamps down. Under pressure, the paste squeezes outward and fills every microscopic valley. And here's a mistake almost everyone makes. More paste does not mean better cooling. It feels intuitive. More paste, more coverage, right? Wrong. Too much paste can actually insulate the chip. A thin, even layer beats a thick blob every single time. The ideal amount is closer to a grain of rice than a coin. Now here's the twist that makes this worth paying attention to. A tube of thermal paste costs $2 to $15. That single tube covers 10 to 50 applications, sometimes more. That works out to pennies per use. Now compare that to what it's actually protecting. A CPU and cooler combo often costs $200 to $2,000 or more. You're spending pennies to protect thousands of dollars of hardware. Skipping a $2 tube of paste is like skipping the oil change on a car that cost you thousands. The math doesn't add up. No paste, dried out paste, and properly applied paste, the temperature gap can be massive. Sometimes 20 degrees or more. And here's the sneaky part. Dried out paste is incredibly common, and almost nobody checks for it. That old pre-built or laptop running hot for years? There's a good chance the paste dried out long ago, and nobody ever thought to look. So what is thermal paste, really? At its core, it's a fairly simple recipe. A carrier base, usually silicone or oil, mixed with thermally conductive filler particles. Budget and mid-tier pastes use zinc oxide, aluminum oxide, or aluminum powder. They're effective, affordable, and what most people need. Premium pastes step it up with silver particles, or even diamond particles in high-end formulas. That's why those tubes cost 5 to 10 times more. Silver and diamond aren't just marketing buzzwords, They genuinely conduct heat better. Physics backs it up. The question is whether that improvement justifies the price for your specific use case. But conductivity isn't the only thing that matters. Viscosity matters just as much. It needs to be thick enough to stay put without running or sliding off the chip, but thin enough to spread evenly under pressure. Get that balance wrong, and even good particles won't save you. And here's what might surprise you. The raw materials themselves are cheap. You're mostly paying for R&D, quality control, and packaging, not the ingredients in the tube. So, does premium paste actually matter? Let's address that directly. For most people, honestly, not that much. A $5 paste versus a $15 paste might only be a few degrees apart. That's not nothing, but not the difference people expect when they're paying 3 times as much. Here's when it actually does matter. Overclocking, where every degree of headroom means stability. High-end gaming rigs running demanding titles for hours. And small form factor builds with tight airflow. In those situations, every degree genuinely counts. Here's when it doesn't matter much. Everyday use. Browsing, office work, light gaming, general productivity. If that's mostly what your system does, a budget paste applied correctly beats an expensive paste applied badly. Every single time. Thermal paste is one small link in a longer chain. Airflow, fan curves, cooler size, room temperature all matter too. Paste alone won't fix a fundamentally undersized cooler. Technique beats price tag more than marketing wants you to believe. Speaking of technique, application matters just as much as the paste. There are a few common methods. The pea-sized dot in the center, the X pattern across the chip, the spread method, using a card or applicator, the line method, straight down the middle. Honestly, most of these work fine as long as you're consistent and thorough. What actually ruins your results isn't the method, it's uneven coverage. Air pockets from bad spreading do more damage than switching to a cheaper paste ever could. A few practical tips before you try this yourself. Clean off every trace of the old paste first, using isopropyl alcohol and a lint-free cloth. Take your time with the cleanup step especially. Leftover paste mixed with new paste creates inconsistent thickness. Don't over-tighten your cooler mounts. That can squeeze too much paste out and create new gaps. And plan to repaste every 1 to 3 years, depending on how hard you push your system. So let's circle back to where we started. The cheapest, least glamorous part in your build has one of the most outsized jobs in that case. It's not about the paste being fancy or expensive, or made with diamond dust. It's about solving one simple physics problem. Air is bad, contact is good. That's it. That's the whole story. Every peak and valley, every degree of throttling, every dollar spent on silver particles, it all traces back to that one idea. It's easy to obsess over the flashiest components, the GPU, the CPU, the RGB, and forget the part doing the quiet work. So here's your actual homework for today. Go check when you last repasted your PC. If you genuinely don't know, that's probably your answer. Next up, if you'd rather get hands-on, how to repaste your CPU in 5 minutes flat. Subscribe so you don't miss either one.